have a data set, and this is from the book Machine Learning Refined. So we have 6 cats, right? So 6 data points. So each data point here, what I call, so this picture here, right there, is what we can call a data sample or also a data point. Okay, it's one example. Okay, and we can just call it, right, like here in this case, it's just image of a cat. Now, your data point or data sample can be anything. It can be a video, it can be a graph, it can be like a signal, like you're registering like a voice signal, it can be text. So this is, a general abstract notion, and in this case we have images of cats. And what we have 6 cats and 6 dogs. So this is, let's say, that's all we have right now. So these are the data samples that we have collected to train our model. So what is the model we want to train here? Let's say in this case we want to do classification. We want to tell apart the cats from the dogs, right? So you want to teach a machine how to do that. Now, if you look at both those, data samples, data sets, you have data set 1, cats, data set 2, dogs. What makes a difference between dogs and cats? What differentiates a dog from a cat? So just for you, I want you guys to look at those pictures and tell me, extract some features, some differences that if you compare visually dogs and cats, you will be able to distinguish between them. So think about it. Look at all these samples and compare the right set with the left set and tell me what makes a difference between a dog and a cat. So easy. No. Ears. Very good. So you said what makes a difference between a dog and a cat. Okay. Something else? What? Yeah, nose. Dogs and cats. So simply you can say ears and nose. Okay? So what you guys have extracted here is like what we call features, like, some characteristics from these data that will enable you to tell them apart. Okay? So we can call these, for example, the size of the nose size, okay, and the shape of the ears, okay. So these two, we can call them both as features. So features is something that you have a representation or an abstract representation. It can be also concrete measurement that you have extracted from the image. So how did you do that? If you go back and you imagine yourself doing it in your brain, so what did you look at? Let's say, for example, here you looked at the nose and you said, okay, a cat, maybe I'd select another color. A cat has a very small nose, so the size might be 1 unit, okay? And then you looked at the dog and you say, probably I'll take this big thing as the whole nose, okay? So maybe it's 3 units. Okay, so that's how you did it in your head. Now, if you look at the other second feature, you have this, for example, the ears. The ears are pointy right there. Okay, they look like triangles. And then you compared them with these dogs. They're like, more like round ears. So this is exactly what you've done. So in your head, you extracted features. So let's call it feature 1, for example. And you extracted another feature, which is feature 2. How did you do that? I have no idea. It's all neural signaling, but that's what we want to teach the machine how to do it. So basically, we want to give the program, the machine learning program, an image like this, and it will extract the features that will distinguish between cats and dogs, right? So you've done that automatically. It's not obvious, but we want to teach the program to do that automatically. We're going to see that, but not today, okay? So let's say somehow by magic, you have a nice program You give it the images, the two data sets, and it will give you, these are the features that will tell apart a dog from a cat. Okay, so now, once we do this, what happens next? So once we do this, let's say, each dog and a cat will be represented by a vector. So here, for each image, so this is, for example, the image that we have, okay? We will represent it as a point and a space, and this point, it's like a vector, so a data point. So one data point, this is my cat, okay? How do I represent the cat? Using two features. What are these two features? The first one might be, for example, let's say the shape of the ear, okay? Shape of ear. And the second feature is the size of the nose. Now, what are those features? They are numbers. They're just values, right? So what you give the computer is just a bunch of values you're playing with. Now, what are those values? I don't know. But for example, here you can put the size of the nose is 1. The shape of the feature, if it's too round, then you can give it a scale from 1 to 10. So it might be, I don't know, if it's like too round, like cat, it's like pointy, so maybe 2, okay? Nose is small, it's 1. So that's how I'm representing the cat. And now you look at the whole thing, imagine all of these guys. Each image will be represented as a two-dimensional feature vector. So all of these guys here will be represented using, a feature vector, if we call it X, belonging to R2, okay? And it has two values. So this is your feature vector, okay? So this is an example of how we extracted a feature vector from an image. So you have a whole data point. You represented it using a feature vector. And generally, we can draw it, flip it, like transpose it, and this is your feature vector, okay? So you can put it both ways, doesn't matter. Now, let's see if what you guys have extracted is good or not. Now, very interestingly, you extracted the right features. So you can see in this book that what they used, the nose size as a feature, first feature, and they used the ear shape as the second feature. And now these are just numbers. So when you have a small nose, like maybe 1 unit, and a pointy ear, like, 2 pointy, like you're gonna put your point right there. So this is, your first data, okay? So all of these are your points, and you plotted them there. What are their coordinates? It's the feature values, so simple. So once you plot them, if you have extracted the right features, you're gonna see that magically all of these guys, they lie in the same, like together on this two-dimensional plane, but in the same region. So you can see that all these, they cluster together, they group together. So this is where dogs, lie on this space. And then you have for the cats, they all lie right there. Okay, so now this is what we have done using what exactly? Using our training data. So we trained our model. Then once you train your model, I'm going to explain more, okay? So you train your model, and your model will draw a line to just separate, create, a separation between these two spaces. So the best thing is like, trying to maximize the distance between these two close points, taking something around the middle, and probably that's your classifier, okay? So now you know that on this side, all the cats will lie here, okay? All cats. So you expect new cats to fall on the left side of this line, and then you expect dogs to belong to this space based on this classifier line. So this is what you learned by training. So how did we train? Now let's explain this. So for training, let's say you have what we have here. Right, so we have an image. So this is your input image or input data. Then we extracted features, right? So we have a feature vector. In our case, two-dimensional, but let's say you have a long feature vector, because generally It might be more than just 2 values. And then this is what we call your x. So this is sample I, okay? So xi. The ith sample in your data. Now you have many other samples. You don't have, in our case, we have 6 plus 6, 6 dogs and 6 cats. But in real life, you're going to have more than that. So this is what we call your X training matrix. So your X training matrix, what is it composed of? So your X training matrix, in number of rows, generally, you put your samples. So you have your samples, okay? These are all your data points. And here, in the number of columns, what are they? What do they represent? Features, yes. So these are the features you extracted. So in this case, if you have D features, then your matrix right there, okay, it will belong to Rn, okay, number of columns times D features, okay? Now, this is your data. This is important. Once you build this matrix in any program, you can do so many things. So this is the input data that you have extracted from the raw data, okay, by extracting features or learning features. Anyway, so your each sample is represented by a feature vector, okay? Now, after that, what do we have? So we want to train a model. So to train a model, to learn what is a dog and what is a cat, what do you need to give it after extracting the feature? So I extracted the noses, the nose, I don't know, like shape, the ear, the ear shape, the nose size, right? And many other features. Now, for the computer to learn, ideally, I would have also what I call the label. So I would tell the computer, for each sample I know that this is a dog +1. And I know that this is a cat -1. So maybe the second sample is a dog too. So -1, +1, etc. Okay? So this is very important. This is this vector right there. Okay? We call it the label vector. So for each sample, for each vector xi, we have one scalar value, one single value that tells us what is the label of this vector, okay? So xi, of course, it belongs to R. So here, dimension 1 times d, okay? So it has d features. Now, what we want to do, is to learn this mapping. So this is the training data. The computer is allowed to see the XTR, okay, the matrix XTR, and it's allowed to see also the YTR, the label vector, okay, for all samples. So what the training model, the black box that we want to train and learn is by optimizing this, by trying constantly to predict labels from input features or samples, I'll try to optimize this, minimize my error. How do I minimize my error? I train my model, I see, oh, I've predicted in the first run of my model, I predicted 1, and then another 1, maybe -1. So I made some mistakes, right? So what I need to do is to make a few changes right there. So to alter the parameters, to change the parameters of my model. So let's call the parameters of my learner are called W. Okay, so these are the parameters of my learner. And this is basically the model that I want to train. So the model is allowed in the training stage, this is very important, to see all the features. So the model can see all those features. And it's allowed also to see all the corresponding labels because this is a training stage. So I'm looking at those and then trying to predict them, changing the parameters of my model, trying to predict again with less, while making less error, and trying to optimize. So this is an optimization process, okay? So the model is trying to optimize or minimize its error, minimize, the error. So we're going to see this in more details, but this is just, an overview, okay? Or minimize its error. So let's say once you have the perfect W, once you have a very nice, W, and your accuracy, you're predicting this, these Y vectors after training your model at maybe 99%. So that's very good training accuracy. You're classifying the training, or maybe 100%. It might happen, but not all the time. But in this case, with dogs and cats, it might be easy with the features we extracted so far. Maybe a bit easy, right? So what you want to keep in mind, we have the training data, the X matrix, and the corresponding label vectors. Now, how can we evaluate our model? Can we say that our model is good just by looking at the error, the mistake, or the accuracy it has achieved using samples it saw? Like, this is something very important. So I want you to think about this just by looking at that, right? So by looking at this, how can you say that your model is good or not?
We need a data sample to test.
Right, so this is, might not be very obvious, but that's what we really need, because how did your model get trained? The model get trained by looking at real samples, right? Okay, remember, real samples, and also, basically samples that have specific characteristics. So these images of cats and these images of dogs. But what if you give your model other kinds of dogs and cats? Will it still, perform at 99%? That is what we need to do. So basically, to train a model, you might have very high accuracy in training, and generally we should, but that does not tell you that your model is really good. The real challenge comes in when you give your model unseen data it has never seen, never used for training, and tell the model, now test your knowledge. Now tell me what's the label for these new samples. Now this is what we exactly do here. So in this case, we have new test set. So this test set was completely hidden, right? So this is important. So you have test set, what we call also hidden set, okay, which means the model never saw or used, okay, during training. Now, if you look at this test set, we have 3 new cats and we have 3 new dogs. What should we do, right, to classify them? Remember, what is the first thing we did? Extract features. We need to represent them, right? So each image, I need to follow the same rule. So I have this image, I look at it, I detect the nose somehow, I detect the ears, I measure the size, the shape, I quantify, the shape of the ears, measure the size of the nose, and then extract my 2-dimensional feature vector. Okay? So I do this for each sample, and this is basically the test set. Then I will give these samples to my model that I trained to output the label. So the basic idea goes like this, okay? So what you do, you train model using what? Remember, the XTR. So this is the training data set, the matrix that has n samples. Each image is represented by a long feature vector using D features, for example, and you give it also the label vector, the YTR, okay? So there are corresponding labels, and this is what you want to learn. You want to learn the model parameters, okay? Call it W, for example, okay, here. So this trained model will output a W, like the characteristics of the classifier, your model parameters. Basically, it's the line, where you put the line on the plane, okay? So, and then after that, so I'll give more examples. After that, what we're gonna test the model. So this is another function. So in test model, what you will give it X test, and you will give it also the learn parameters, okay? And you'll give it these 2 things. This is your new test set. So how many testing samples we have? 1, 2, 3, 4, 5, 6. Okay? So you'll give it a new matrix that has only 6, samples, testing samples. And the dimension of X test in this case is 6 times 2, okay? Because we have just 2 features. We extracted 2 features, okay, from each of those guys. How many guys we have? We have 6 from these, right? So your dimension of your X test is 6 samples times 2 features in this case, okay? And then what will your model predict? It will predict, this is very important, what will it predict? What is the output? What do you want to do to these testing samples? You want to predict if they're dogs or cats. So for each guy right there, you want to say this is a dog or a cat. So you're gonna output a Y test, okay, predicted, label that tells you, I think that this is maybe a cat. I think that, the other one, this is a dog, -1, okay? So it will try to predict. What is the dimension of your test label vector to predict here?
65.
Yes, very good. So here it's like has 6 elements, so 6 times 1. So this is, your Y basically test, okay? So that's how all machine learning generally works. It's a simple concept. So you can see how you do it. And this is, one type of machine learning, but for now we're focusing on this, okay, once you have labels. Now let's look at the results of the classification of these guys. What do we have here? Okay, you can see that, well, this is the parameters. This is what I learned. This is my W. My W gave me that I need to put my line right there at, I don't know, whatever, this angle, at this position, right? For example, just saying, right? Now, once I apply put the features, plot my coordinates of this new body right there here, does it lie on the left side or on the right side? It lies on the cat side, so it's like it's misclassified as a cat. Now imagine somehow how can we solve this problem in a better way? How can we solve this problem in a better way, guys?
Add another feature on this model.
Yes, extract more features that will enable this poor doggy to be classified as a real dog, right? So you need to think about how to design or extract better features. When you plot this, dog, it will be on the right side. There's another alternative. Let's say that's a good thing. So design better features, but we can also do something else to further improve this. Maybe
We can change
the W. Yes,
angle.
the angle. Very good. So we can change the angle. We can basically go from here and maybe put something right there. Well, it's not ideal in this case because you see like the space for the cats, it's very narrow. But if I move the line and I keep the same, right, testing samples, like training data, so I can classify it as a dog. Okay, so now what we're gonna talk about is, right, so this is, just a simple, very simple example, a toy example for machine learning. But what we might be facing is something that looks like this, right? Now, for you guys, if you look at these benign cell samples, right? Benign cancer samples, this is histopathology images of an organ in the body, right? So you have you have benign and you have malignant, right? So even if you look at this, you have not been trained. You haven't seen many examples to learn to tell apart the benign from the malignant. It's so hard for you to do so, right? Even right now. But what we want to do, you want to give more data to the computer to learn how to tell apart the malignant from the benign. And the question is, what kind of features I would extract from these images. So you can see sometimes it might look simple, but it's more complex, right? So now what we're going to talk about is, right, we talked about extracting features. So another way of extracting features, I just wanted to give this. So in your case, in the first case that I explained, what we did, we focused on two things, right? So if I do, right, we focus on the nose, right, and on the eyes, right? So we focus on these two. But what we can possibly do, something else. So we can, for example, what we say vectorize the raw image. So we can, instead of extracting features, the features can be the intensity themselves. Like, for example, right here, if I'm going to edit this, and then select, let's say I want to classify if a small region or a patch in this image, here I think it's 16 by 16, belongs to the dog, like the foreground or the background. Is it a dog or not a dog? So a dog is like, you know, this whole shape, and not a dog is the background, right? So let's say I extract this patch, right? And then what I have, you can see I have this patch right now. How many, what is the dimension of this patch? Let's say it has 16, sorry. It has 16 by 16 pixels. So the easiest way, let's say we're using a very naive approach, is to vectorize this patch. So I'm going to vectorize it. Okay, so I will turn this patch, this small image, into a long feature vector. How do I do that? I read each value here, okay, one by one, and I copy them here, like in the vector. So I go read the image line by line, and first line, then I move to the second line, and I'm going to put all these, you know, values right there. So this feature vector, it's like 16 times 16, right? So it has 16 by 16 elements. Now, the thing is, now when I say I extracted features, so in this case, what are my features? Colors, intensities, right? Values, colors. So I just directly took the whole, like, you know, just intensities. I did not detect anything in particular. So what you can do, you can, you know, do, you know, you can use this strategy too to simply extract features in a very simple way. And we use this a lot in machine learning, like, in treating or processing medical data. So sometimes we extract some fancy features, other times you can just take the raw values, because the raw values will tell you something about the characteristics of the tissue of the brain, whether it's, so if high intensity, it means, for example, white matter, very low intensity gray matter. So intensities are important in images, okay? Now, very nicely what we talked about, okay? So this is, you know, how generally machine learning program works. So you guys can see, so you define a task. What is the task we looked at today? The simple example is classification, okay? So we want to classify. And then what we did, we collected data, right? So we had what we call a training set composed of, you know, 6 dogs and 6 cats. And then we have another hidden set that we kind of put apart, right? Like for training, for testing the model. Good. Now what we did, we designed features. We said we're going to somehow magically detect noses, detect ears, extract features, and train the model. Once I train the model, I give it the new testing set, and I classify on unseen data. Now,